So, have you ever actually stopped to think about how your computer knows the difference between the letter A, the sound of a dog barking, and a vivid high-definition photograph? I mean, on the surface, these are completely different sensory experiences for us, right? But deep down inside the hardware, your device sees them in exactly the same way. In today's explainer, we're going to absolutely unravel this fundamental mystery of digital media.
Welcome! Today, we are looking at the foundations of digital data representation. We're going to peel back the screen and see exactly how computers take the messy, vibrant, real world of sights and sounds and translate it into a language they can actually understand and process. Okay, let's dive into this. Here is our roadmap for today. Number 1, the binary foundation. Number 2, translating text and emojis. Number 3, capturing sound in bits. And finally, number 4, painting images with pixels. Let's get right into it. Starting off with section 1, the binary foundation. This is the absolute basic rule of all computing. Here is the core premise that unites absolutely all digital media. All text, sound, and images must be converted to binary to be processed by a computer. That means literally everything you experience on a screen, every article you read, every single podcast you hear, every high-def video you watch, ultimately comes down to processing binary bits. It's the universal translator for your device. So whether you're holding a top-of-the-line smartphone or using some 10-year-old laptop, beneath that slick user interface, it is entirely just a sea of ones and zeros crunching away. Let's move on and see how this builds into our second section, translating text and emojis. We're going to start with the simplest form of data representation. To really understand how computers read text, we have to compare character sets, specifically ASCII versus Unicode. Think of ASCII like a basic box of 8 crayons. You know, it gets the job done for standard English text, but the range is highly limited. But the world is vast. We communicate in thousands of different languages, and obviously, we constantly use emojis. That is exactly why your computer uses Unicode. Unicode is like, actually, scratch that. It's more like the Mega 128 pack of crayons with a built-in sharpener on the back. It allows for a massive range of characters. But there's a crucial trade-off here. Because Unicode represents so many options, like that laughing crying emoji you just texted someone, it requires more bits per character. You gain incredible variety, for sure, but you have to spend more data to get it. Moving right along to section 3, capturing sound in bits. We are transitioning from static text to continuous audio now, which presents a really fascinating challenge for a computer. Think about sound in the real world. It is a continuous wave, right? But a computer cannot process infinite, continuous waves. It only speaks binary. So how do we solve this? Well, we sample the sound wave. Think of it kind of like taking a flipbook animation of a moving object. The computer takes tiny, rapid, frozen snapshots of that sound wave. Once those individual snapshots are captured and converted to binary, the data can be processed and stitched back together so you can actually listen to your favorite song. To really wrap our heads around this, we need to define 2 key terms, starting with sample rate. Sample rate is simply the number of samples taken in a second. Think of it as how frequently the computer is checking in on that sound wave to record its exact position. Just to put that into perspective, standard CD quality audio samples the sound wave over 44,000 times in a single second. That's mind-blowing. If you take fewer samples than that, you end up getting that muffled, robotic sound of a bad phone connection. And then we have sample resolution. Sample resolution is the number of bits used per sample. So the crucial point is this. Once the computer takes a snapshot of the audio wave, the sample, it needs a certain amount of bits to store the precise detail of that specific snapshot. If sample rate is how often we take a picture of the sound, sample resolution is how sharp and detailed each of those individual pictures actually is. When you put those 2 concepts together, you get this ironclad rule for digital audio. A higher sample rate plus a higher sample resolution equals higher accuracy of the recording. You're taking more snapshots, and you're using more bits to describe each snapshot perfectly. But there is that trade-off again. Capturing reality this accurately requires more data, which inevitably means the file size increases. Higher quality simply demands bigger files. And this is exactly why downloading a high-fidelity, lossless audio track eats up your phone's storage space so much faster than a standard compressed MP3.
This perfectly sets up our final visual section, section 4, painting images with pixels. And you're going to know this pretty quickly, that visual fidelity operates on the exact same logical rules we just saw with text and sound. Let's logically sequence out how a digital image is formed. First, an image is established as a series of pixels. Think of it like a giant, microscopic mosaic made of tiny square tiles. Second, the specific color of every single one of those tiles is converted into binary code. And finally, just like our sound waves, that massive grid of binary data is processed by the computer to display the photo on your screen. Now, just like with audio, we have a way to measure the detail of this translation. For images, we use resolution. In a visual context, resolution is defined as the total number of pixels in the image. The more pixels you have, the tighter the grid and the sharper the detail. I mean, this is exactly what you're paying for when you upgrade from a standard 1080p television to a 4K screen. You are quite simply buying a much denser grid of pixels.
Alongside resolution, we also have color depth. Now, what's really interesting about this slide is how beautifully simple the math is. Color depth is just the number of bits used to represent each color in a pixel. If you only use a few bits, your computer's basically painting with that small 8-pack of crayons we talked about earlier. But by using more bits, you unlock millions of distinct shades and gradients for just breathtaking realism.
Which brings us right back to our recurring digital motif. Higher resolution plus higher color depth equals a far better, more lifelike image. And this brilliantly illustrates the ultimate digital trade-off that governs all our technology. As quality increases, the file size inherently explodes. Whether you're jumping from basic text to emojis, increasing the sample rate of a podcast, or shooting a photo in higher color depth, mimicking reality always costs more data. So everything, text, sound, and images, boils down to processing binary data. And better quality always requires more data, which leaves us with this really fascinating question to ponder. As we continuously demand more and more perfect digital accuracy in our media, and as our files get larger and larger, is there a physical limit to the amount of binary data we can actually process? It is definitely something to think about the next time you stream a massive, high-definition movie right to your phone. Thanks for joining me on this explainer, and I will see you in the next one.